Well, hello friends. Welcome back to the program. Today we're going to take a look at memory usage on Twitter, which I've noticed is pretty big. So we need to do something about it. And I already have some ideas for what we're going to do, but let me visualize it for you. So we're going to use heap track, which is a Linux thing, and we'll start Ladybird so that we get a web content process, and then we'll attach heap track to the web content process, and then navigate to somebody's Twitter profile so that we can run some JavaScript and just generally exercise our web engine a bit. We'll let it get to a steady state here. Definitely taking a bit longer to do everything when you're running with heap track attached, because it is instrumenting all of the allocation activity. Also, we do have some visual regressions on Twitter, I see. Probably from recent changes to overflow and absolute positioning. Anyways, that's not what we're here for. We loaded the page enough, so let's stop it right there by just exiting. And then since exiting Ladybird will also exit the web content process, heap track automatically throws up a GUI that gives us a choice of interesting visualizations. And consumed here shows you memory usage over time. And if we just hover here, we can see that we're looking at 330 megabytes consumed in total. And then I think these are like some of the larger allocations, sort of where they come from. So you see them as well, but the top thing here shows us the total, which is what I'm interested in primarily at the moment. So 330 megabytes is roughly where we get to after the page finishes loading. And if we go to the bottom up tab here and flip these over so we can see sorted by peak, and then we can see every sort of stack that led to the allocation responsible for most of the memory usage. So we see that we have 64 megabytes roughly allocated with this particular stack here that bottoms out in create AST node JS identifier. So we're creating AST nodes, and roughly the way to read this is just you have about 64 megabytes worth of identifier AST nodes. And then if we continue looking here in the list, we'll find other AST nodes like member expression, call expression, and so on. All of these in the double-digit megabytes. And there's just a ton of different AST nodes in this list. So this is an observation I've made in the past, and we've talked about ways to address this, but nobody ever actually picked it up to work on it. So I thought, hey, why don't we pick this up and work on it and make a video out of it? So the object of today's video is to reduce the memory usage of our JavaScript AST, because as you can see here, it is the single biggest contributor to memory usage on a complex website like Twitter. There's other stuff here as well, like backing storage for function environments, JavaScript objects, and so on. But the AST nodes really do stand out, and I'll show you what they look like. So if we go to JS AST node, we can use the nifty hover thing in CLine here, which tells us that they are 80 bytes for a plain AST node, not even a subclass that has something interesting in it. So the biggest one was identifier, and we have 633,900 identifiers allocated at the point where I control seed Ladybird. So it's quite a lot of identifiers, right? And we can look at identifier right here. And identifier is 128 bytes. So quite a chunky boy. So it's actually an expression. Expression is an AST node, and it doesn't add any more members. So on top of expression there, identifier adds a bunch of stuff like the string that it represents, and then potentially if the identifier refers to a function call argument, or rather if it refers to an argument within the current function, then we have the argument index here. And if we've done a lookup of this argument, then we have a little cache location where we can, if we've done a lookup of the identifier, then we have a cache for its environment coordinate. And all of these things take space, but I think today I'd like to start at the AST node itself, because that is the base class for all AST nodes here. So if we can shrink AST node, that means that we'll use less memory for all of these things. And AST node, as we mentioned, is 80 bytes. And there are some things that are really silly here, which you're going to see now. So the big member in AST node is called the source range, and it is 64 bytes. And by the way, we already have 16 bytes before the first member. That is because we inherit from ref counted, which uses 4 bytes for the ref count. And then there's also a vtable pointer, because this is a virtual class hierarchy. So that plus padding means that the first member here comes in at the 16 byte mark. So offset is 16 bytes. Size is 64 bytes. Now, why is the source range 64 bytes, you might ask? And this is basically why. So a source range, which we store for every AST node, is the file name as a string view. So that's the sort of the name of the JavaScript file that this AST node is in. And then a position start and a position end, which is just where does this AST node start and end in the source code. And positions are this thing. So line, column, and offset, all of them size t, so 8 bytes each on 64-bit, which means that they're 24 bytes per position and 16 bytes for the string view, giving us a total of 64 bytes. Yeesh. Okay, so this was basically the observation I've made in the past, and look how big these are. But what can we do about this? Well, a lot, actually. So storing the file name like this, it uses 16 bytes per AST node just for the file name, because the string view is a pointer to the characters of the string and then also a size, right? So standard string view. But we could easily reduce that to one pointer if we have all of the AST nodes point to a common location instead where this is stored. So that would cut one pointer out. And then these position things, certainly we probably don't need 64-bit values for these things, right? Because are you really going to have more than 4 billion lines in your JavaScript file? I hope not. But if you do, maybe that's something we don't need to support. Or at the very least, maybe that's something that we don't need to emit accurate line and column numbers for if you throw us a 4 billion line file. So I'm thinking these could be U32, which would cut down the size in half, right? And then furthermore, the line and column of each position, they're really just a sort of something that we can compute, right? Because we have the offset, and as long as we have the offset, if you need the line and column, we can just figure out the line and column by processing the original source code and figuring out the line and column for the given offset. So all of that to say, here are the things that I want to do today, and it's going to be a bit messy, I think, but I want to, instead of this thing containing the file name, I want to point to some kind of shared like source code object or something like that, like code, which can then have the file name in it. String file name, something like that, right? Because a pointer to code, that would only be 8 bytes instead of 16. And it has the nice added benefit that now we can put an owning string here. So we don't need to rely on somebody else keeping this, whatever this file name string view was referring to, we were relying on somebody else keeping that alive. But by doing this instead, we don't have to worry about that. And in fact, we can do the same thing with the actual source code. So something like code, right? And this would contain sort of the whole program string that we parsed. And then the offsets will be offsets into the code string. And I think I've described this idea to multiple people before, hoping that somebody would get yak baited, but nobody ever did. So this is what happens if nobody takes your yak bait. Eventually, you have to shave the yak yourself. Okay, so let's see. So what do we do? So instead of saying, actually, maybe we can keep this API. This source range class can continue to exist actually, but instead of having a file name, it will just have a code pointer like that. Okay, and then we need some kind of API somewhere. Wait, where do we need the API? Maybe the source code could have an API for like source range from offsets. And then if you pass in a start offset and an end offset, then we will calculate by doing something. We'll figure that out later. But yeah, something like this. And I guess this could be a big boy class, actually. There's no need for this to be a struct. Something like this. And why don't we make a little helper for creating it? Create file name string code. All right. String code. Okay. And we'll also add some accessors here just for good measure. And at this point, I'm starting to wonder, why isn't this in its own class? Let's just put it in its own class. So let's see. Lib.js. I guess this goes under, oh, parser doesn't have a subdirectory. Okay. We'll just call it source code. Seems all right. Source code A. Okay. And we take that. And now we just need a forward declaration for that thing, actually. Libjs forward. Ta-da. Where can I put this thing? Source text module class source code A. Okay, source code A dot h. Okay, so far so good. A little bit of pragma, a little bit of namespace. Okay. and a little bit of libjs forward. What else do you need? A little bit of string. And we also need to know that source range is a thing. We can put that here, I think. Source code, source range. Okay. Yep, looking good. So yeah, and then we'll have to implement this, but I think we'll leave that for last because need to figure out how to actually use this thing and where to put it into everything. Source code. Okay, and then we'll just do something like that for now. We'll come back here. Okay, so now that we've invented this and struct source range. Oh, I need to be consistent about forward declarations. Maybe you could let me click on you to get to the thing. I guess not. Okay. So I was just thinking these could be U32s, but maybe it doesn't matter because the AST node, instead of storing a source range, because this thing is chunky, right? It's 56 bytes now. And instead of doing that, we could also just store the individual parts here. So like source code and start offset and end offset as U32s. And then this API right here, instead of returning a reference to a source range, we can just synthesize one and return it by value. And this mutable API can't exist because we don't have a source range. And then what if we just move this out of line and figure out what to do with that later? But yeah, the constructor takes a source range. Okay, so we probably get source ranges from the parser then. And everybody gets a source range and they just pass it up to their superclass, so it eventually ends up in AST node. Okay. All right, so hypothetically, if we do this, then AST node becomes 32 bytes, which is what was it before? I already forgot. 72 bytes. And that was after I tweaked source range to not have a string view. So it was 80 bytes originally. So it goes from 80 to 32. That would be a very, very tasteful reduction, I feel like. I'm gonna do math here because I don't trust my brain. So 48 bytes per AST node in like less memory usage, right? So hypothetically, say that we have 633,900 identifiers. So if you multiply that by 48, that's like 30 megabytes less memory used just for these guys right here, not to mention every other AST node. So this would be fantastic if we can get this working. We should be able to substantially reduce this. What was the number? 330 megabytes, right? Yeah, so just from the identifiers, we should be able to get down to 300. 300 and more. So let's see. Of course, now that come all the practical details. So did not think this far ahead, but hopefully the pieces will just fall into place. Okay. Forward declaration invalid use, source range. Okay, so we might need to put the source range destructor out of line. Bum, bum, bum. Alternatively, we can also just include source code here. Maybe that's fine. I mean, we're going to need source code anyway in places, or maybe we're not. Okay, let's see if we can avoid including it everywhere. That would be the coolest. Where am I needing it? Okay, maybe that's not a thing I need to go down right now, and I should just accept this. Maybe that's okay. Okay, so this is going to take a hot minute, that's for sure. I do have my trusty 2-computer compile cluster, so at least, yes, it's up and running. So at least we should be able to build a little bit faster. Parser, okay, right. So now something broke in parser for sure. Oh, look, 155 errors. Cool. No matching constructor for program. Cannot convert initializer list argument to source range. Oh, the first thing is a source range, of course. Program wants a source range. And we are just passing the file name, which we can't because it expects a source code. So what if we just imagine that the parser has a source code somehow? Let's see, parser, members. Let's see, all right. We will give you a ref putter to source code. Source code. Okay. Now the parser has a source code. We'll populate it later. Actually, this makes me wonder, this should probably be a non-null ref putter because source range can't refer to an invalid source code. Yeah. So then we'll do this. I think that'll be okay. And then we have 154 problems to resolve in this file, which is going to be super fun. They all kind of look the same though. Maybe we can we do something like this, like a multi-cursor editing, 154 places at the same time? That would be real nice. Okay, so now, hopefully this works. Ooh, it's sluggish. So m source code. Ooh, look at that. We got them, all except one, which is just, didn't have that exact syntax. Okay. Okay, that was really nice. Shoutouts to all the people who kept telling me to learn multi-cursor editing in C-Line. I'm glad that I did, and I'm glad that you kept nagging me about it. It's definitely super helpful in many situations. Let's see. Okay, so we have errors in markup generator. Line 153. I mean, it's right here. Source range.file name, of course, is no longer a thing. Instead, we have to do code file name, just like that. No big deal. Maybe we should build with K0, just so that if we hit errors, it will just keep building. Use if deleted function in error.cpp. 70. Okay. We might not have an AST node associated with the execution context. A meaningless source range is fine. Well, we can't make an empty source range anymore because we have to have a null ref footer there. So I guess trace back source range. So let's see. So if you have a backtrace where one of the frames does not have a valid source range, we could make it optional, but then we have to deal with that everywhere. Okay, I'm just gonna take the easy way out here and make a static dummy source range. How do you make a source range? You just make one like this. Code. Yeah, so I just use like empty strings. I think that could be okay. Dummy source range. Okay. Code file name. Oops. Actually, we could make an accessor for the file name. Maybe that would be the polite thing to do. That works. It's gonna cost us a little bit of rebuilding, but it's probably a nicer API if you can just do file name paren like that. Just looking for the other place where I did this. Yeah, so I don't have to do that. Okay. Okay. And then we build and we build. So how does the parser get the source code to be in that member? I guess when we construct the parser, we can just make this thing. So like, what if we just say like m source code, create lexer dot file name lexer dot source? Does that work? Those are string views though, so that'll make a copy. That's not super slick. What if we just use string all the way for these? I think that'll be a bit nicer, because then they're owned. And yes, if you try to pass a string view to the parser, then we will make a copy of it, store that inside of the lexer, and then all of the AST nodes will keep that copy alive. But it's the much safer thing to do. So let's see, what's that error? Exception reporter. Let's check that out. Oh, just another file name. No biggie. Let's see. So now I made the parser created in the constructor initializer list. So I could actually do that. Because yeah, if we do that, we can just say m source code instead of star m source code, right? So we don't need to dereference if it is a non-null ref footer. So it's a tiny bit nicer. Yeah, Yeah. Okay. And then what am I missing now? I mean, we didn't figure out how to actually map from the offsets to the line and column yet. But yeah, we have more errors. So let's deal with errors first. VM CPP uncatched. I think that wants to be uncaught, but I'm just going to ignore that. Also, what's a mulde? I should probably say module. Anyway, let's not get caught up with the spell checking. Source range. Wait, oh, you're trying to take a reference to source range? Well, that's not going to work. I can't give you that. I can give you this. And then this guy just wants to do that. Yeah, that's okay. No big deal. Okay. Let's see how ice cream is doing. It's pretty busy. Busy on my little compiler network here. Let's see. I keep looking at this for some reason. I'm just gonna put that over here. Okay, just keep on chugging. So what was I talking about? The mapping from offsets to line and column, which I added API for that somewhere. Not in source range. Source code has a range from offsets. Right, this fella. So I guess while it keeps building, we can try to figure out how to do that. So I have start offset and end offset. What do I do to turn that into source range? To turn that into a source range. So return source range, something like this, start, end, position, start and end, and then we have code. So we have to iterate, yeah, like I guess you could cache this information the first time you ever get it. Like if it turns into a performance bottleneck someday, we could totally cache sort of offset to line number mappings. But I think unless you throw an exception, you don't actually need the line and column in most JavaScript that we execute. So let's see. So what I want to do here is I want to make a UTF-8 view over the code, and then I want to iterate. I want to iterate over the begin IT view end, because I know the UTF-8 iterator has some magic thing to get the byte offset out from it. So like if, or wait, no. What do I want to do here? I want to keep track of what's the current line. I guess starts at 1. Current column starts at 1. These 1-based line and column numbers, I find them extremely easy to mess up with a Thinko, but let's try to keep our heads cool here. So let's see, if we hit a new line, then line plus plus, or even plus plus line, if you will, column resets to 1, and then we continue. Otherwise, plus plus column, right? And then here, before processing the character, we check. So if start offset is what is the view dot byte offset of iterator? Yes, that's the magic API. Yeah, and it's just a simple subtraction, so it doesn't do anything fancy at all. So here we can just say start is position. I guess line is line, column is column, offset is start offset. Yeah, we already knew the offset. Okay. We do exactly the same for the end. And when we find the end, we can just, not return, but break out of the loop. Okay. This feels sound. Certainly not efficient because you end up scanning through the whole thing. So like caching it so that you could do a binary search or something through a sorted list of, or a sorted array of these mappings could be faster, but in general, I think doing this kind of lookup is sort of in the realm of diagnostics and JavaScript errors and exceptions. So they're a pretty rare case. At least I know that in WebKit for JavaScript Core, we did something kind of similar to this. And the reasoning there was that like, that's the rare case. So let's optimize for the common case. So I'm just bringing that sort of thinking to the problem here. Okay, so that built. Google.com crashed. Oh, that's kind of funny. We don't crash right away, but we crash later with a missing symbol. Interesting. It's a bit funny that we don't eagerly try to bind, but whatever. That's not what we're here to worry about. So we're missing source code create. Sure. I guess I'm missing a lot of things in source code. Source code default. Oh, did I not specify that even? I didn't. Okay, never mind. Create. Code is adopt ref new source code A. Move the file name and move the code. Actually, can I just do that? Don't need these. Filnam and code. Cool. Did I missing these two APIs as well? Right. Source code. All right, look at that multi-cursor action. Almost. I'm missing an end paren right here. Okay. Oh, I'm missing AST node construct from source range. Right. Because I just said, yeah, I said we'll figure that out later. All right. I guess now it's later. Okay, so we need an AST node constructor. Source range that takes the source code from the source range. code. Yeah. And what did we call the others? Start offset. Start offset, like that, right? So the parser will give us a source range, but we'll just take out the bits that we care about. Like that. And we can just translate them later. Later when somebody asks for it. Wait, how do they ask for it? Oh, this thing. Right. Right, I never implemented that either. Okay. So this is how they're going to ask us for the source range, which we could previously just return as a const reference, but now we have to make one. So we just say source range, source code. Or wait, no, we call that API that I added. Source code, range from offsets. Yes, yes, it all falls into place. Come on. Okay, okay, we're good. We didn't crash. Let's test it out. So, and also let's let's build the JavaScript test suite, at least our small test suite, so that we can just smoke test it. But that's pretty cool. So let's see if we can heap track this thing. Let's see, heap track p pid of web content, okie mokie. Okay, loading, and we crashed, damn it. All right, oh shoot, undefined symbol. Okay, well, I should have seen that coming. Source range file name. That is indeed unimplemented. Source range doesn't have a corresponding CPP file. Okay, fine. I'll just put it here for now. Code file name. Okay. Let's try that one more time. Did I finish the oh, building test.js failed because of it fails with the undefined reference. So I would have noticed if I let this finish. Let's see. Test.js. Taking its sweet time. No errors. That's a good sign. Okay. So let's try to Ladybird once again, and we attach heap track and load the tweeters. And then we just let it run. So if this works, in theory, it should give very good results because we reduced AST node from 80 to 32 bytes. So 48 byte reduction, as I recall. Okay. Let's let's let it load this extra scripts here and whatever. We don't want to skimp on it or like quit too early. Okay. It stopped talking, so I think we're good to quit there. And how does it look? Merging allocations. All right. Consumed. Hello. 253 megs, down from 330. That is a sizable improvement. 330 down to 253. 330 down to 253. 77 out of 330 is about 23% reduction. That is a respectable reduction. So if we look at the bottom up here, and yeah, AST node identifier is no longer the top contributor. Now it's array allocation instead. So that's still near the top, but it is definitely better. And we still have the same 633,900 number of allocations as in the first run, right? Or am I looking at the same run? No, it's the exact same number of identifiers. So we know that we have most likely parsed the exact same code. It is a little bit shaky sometimes when you're working with a live site, but the exact number of AST parse nodes is a good indicator that it's a stable-ish result here. So yeah, we cut, for identifier alone, we went from 64.4 megs to 40.2. And second biggest member expression, we went from 18.6 to 10. So almost cut in half. It's very, very good. Cool. I mean, most likely, or absolutely, without a doubt, there's more stuff we can do here. But let's see. Let's start with commit at this point. Okay. And I mean, this all has to go in and come in one big commit. libjs. What do we say? Reduce memory AST memory usage by shrinking source range by shrink wrapping source range info. AST nodes. For this change, each AST node had 64 bytes worth a 64 byte source range object, source range member. The source range had, this source range had the following layout. So file name, string view, 16 bytes. Start position, what was it? 24 bytes. 24 plus 24 for the end, right? Am I remembering that right? Position here, 24, yeah. So we don't actually need to shrink this because now we just synthesize it, right? It's never actually stored with our objects, so it's fine for it to be large. This made the AST very heavy. Okay, wait, no. To reduce memory consumption, the AST nodes now only store the following: source code, no ref putter, and start offset. Probably we're gonna need it to do a little bit of editing here. just so everything aligns neatly. End offset, 4 bytes. Each the position structs have line, column, and offset. All members size t, or 8. Yeah, all. Okay. Source code. It's a new ref counted data structure that keeps the file name and original parsed source code in a single location, and all AST nodes have a pointer to it. This, yes, the start offset and end offset can be turned into line and column when necessary by calling by calling source code range from offsets. Is that what we call that? Source code, where are you? Range from offsets, yes. So, yes. So this will walk the, this will recompute or compute the line. This will walk the source code string and compute line column numbers on the fly. So it's not necessarily fast, but it should be rare since this information is primarily used for diagnostics. Error stack traces, or exception stack traces. Right. Okay. And then the above with this AST node shrinks from 80 bytes to 32 bytes. This leads, this gives us a 23% reduction in memory usage when loading twitter.com/awesomeclaim, the world's most important test case. I feel like I've used that as a test case a million years ago in WebKit. Do I have WebKit here? Git log. Twitter.com/awesomeclaim. No, it's not in here. Ah, dang it. All right. I feel like I did that at some point. Anyway. Yes. That's pretty cool. Actually, we should note what the exact numbers were. So 300 MIBs before, 253 MIBs after. Nifty. Am I saying the number right? What was the consumed? Oh, actually, I can read it right here. 330 and 253. So good. Very, very tasty. Okay, just gonna drop that there. And then let's just take a look at identifiers a little bit more, because I feel like, wait, this is the 253, yeah. So identifiers, still heavy, 40 megs. And I bet you we can do some easy shenanigans here and reduce it further, because it is 80 bytes. Right, 80 bytes. And we have an optional lexically bound function argument, optional size t. So optional size t is already going to be pretty heavy. That's like 16 bytes. And I'm not sure we even use this for anything. I think it was for an optimization that we wanted to add at one point, like back in, I think it was in October of last year. We wanted to do something with this, but I'm not sure we ever finished that. I think we reverted it. So it might be that this could just be deleted. That would be super ideal. Is anybody accessing it? It doesn't have an accessor. Okay, what if I just yeet this thing? That would be very nice if that just works. Then we would get 16 byte more per identifier. Wait, what was it called? It was called lexically bound function argument, right? It's set by the parser here. That's the only thing this loop does. Identifier and argument index associations. So I think that's what's being set, and then nobody was using that either. So maybe we can stop tracking these. Associations, what the heck was it called? Wouldn't that be nice? Oh, here's an API that we can maybe delete that nobody calls. All right, all right. Okay, well, it's going to take another hot minute to rebuild with these changes, but if that works, which I feel like we should have noticed this a long time ago, but whatever, we're noticing it now. Nobody uses that, I think, maybe, hopefully, which will give us 16 more bytes per identifier. So we can do some back of the envelope math here with BC, the back of the envelope calculator. So that many times this many. So potentially there's another 10-ish MIBs here. How many MIBs exactly? Well, 9.67 MIBs. We'll see though. But if, yeah, another 9.5, almost 10 MIBs, not going to complain about that. And then we have this fella, the environment coordinate, just 24 bytes. Could definitely make that smaller as well. Because I don't think these need to be 64-bit numbers. They could be, so what these are, they're like referring to nested environments. So if you have something like this, and then function bar like this, then there are nested environments here. So if in bar you were to access A by saying like A+1, now you're accessing something from the outer environment. So it's one hop out from the bar environment. So you have to make one hop to get to foo. And the way that we cache lookup for this variable here is that we cache how many hops you have to make on the environment stack, if that makes sense. in order to get to the value that you want. So the environment coordinate, the hops, is like, how many hops do I have to make? And for this, if we make this a U32, that means that you could only have a nesting level of up to 4 billion something functions, which I feel like is a reasonable limit to have. And likewise, index is like, that's the index of variables in that environment. So say that you have something like this. So now you have 2 variables in that environment. So you would need to have over 4 billion something variables in order to overflow a U32 here. So it does seem a bit like this doesn't need to be 8-bit or 8-byte values, 64-bit values. And it probably doesn't need to be optional either, because optional, in this case, optional uses up another 8 bytes just for that little Boolean flag that says, oh, this optional is empty or non-empty, or has value or does not have value. So in fact, I mean, yeah, this should be a separate commit, but I think, yeah, we can shrink that down. So it's, instead of having an optional environment coordinate, we would have 2 U32s, and then we can have a magic value like this, but not get another magic value that just means that it's invalid or unset, right? Because then the whole thing would shrink down to 8 bytes total, which would save us another 16 bytes from the 24 that it's currently using, which would be another 9.67 MIBs saved. So I bet you, yeah, this thing is looking like it's going to pan out. So I'm real stoked about that. So let's see. Lib.js. Remove unused argument lexical argument index metadata from identifier. This shrinks identifier by 16 bytes. That's great. Yeah, that is great. And assuming that it compiles, that is, but if we made it this far, because now it's compiling libweb, I feel like we're going to make it all the way to the end. So this will be a bit more involved though, because now we need to make this a little bit smarter. So I'm going to start touching it once this thing just compiles so that we know that it worked out. This right now reminds me so much of my work at Apple. This was basically identical to the type of stuff I was doing at Apple. And it's a lot of fun. Especially like the wins here are ridiculously huge compared to the type of stuff I would spend weeks on getting in WebKit. Like there was no such thing as a 23% memory usage reduction. Maybe once a year you would look out and, yeah, we were in the 1% range typically with the optimizations we could do. Which is, by the way, an interesting point that somebody brought up on Discord the other day that, I think it was Andrew, saying that it's interesting that people come to Ladybird and they think that because it's a new browser engine, it's going to be like more lightweight than Chrome or WebKit or Gecko, when the opposite is quite true. It's actually way heavier because we haven't done memory optimization, and the production engines have spent years, decades, doing sophisticated memory optimizations. So if you're looking for a lightweight engine, we are not that, not yet. We can absolutely become lightweight, but that's going to take some real work, even to reach parity with existing production engines. It's going to take some serious work because they do a lot of smart, clever stuff to reduce memory usage. So let's see. Okay, well, that built. And google.com is my official smoke test, and it works. Okay, so let's just keep rolling, because that means that nobody was using that. We're probably just good. Okay, so what do we do here? We turned these into U32s. Wait, what was the size of identifier before I started this? Identifier. Hello. Okay, so the size is 64 bytes. Right. So we turn these into U32s, like this, and like that. And then we can also make an like an invalid marker or something. Something like that. Maybe we'll have a little API for convenience. So if hops has to be not invalid marker, and index has to be not invalid marker, sure. And then they will start out being the invalid marker, and we have built ourselves a class with a built-in empty state or a built-in invalid state. Now, normally I don't love doing this kind of thing, but since this unlocks a serious memory savings thing here, where we can save almost 10 megabytes on something, then I think we should still do it. So environment coordinate, we remove the optional wrapping, and that leaves us with 8 bytes. Identifier is down to 48 bytes. Very, very nice. Now we just need to figure out what to do with the breakage. So instead of has value, we just check is valid. Sure. We could even call it has value if we want it to be real fancy, but is valid is probably okay. And don't need the arrow to dereference. Okay, assigning from an optional, sure. And once again, a big heavy rebuild, of course. Actually, maybe we only need to, let's see if we can just rebuild the JavaScript engine, because that's a bit smaller. If that works, then, and we know that if this works, and the tests pass, I do feel pretty good about it. Yeah, this seems like a really obvious thing to do, actually. It's silly that we made that thing take up a whole 24 bytes. Now I'm just thinking, like, what else could we do to AST node to shrink it? Because it's pretty shrunken now at this point. You know, we have 16 bytes of data here. You don't really want to go smaller on these, because it's perfectly feasible that you would have a line, like you can't go U16, right? Because you could definitely have something with more than 65 or 64K columns. Like you see that frequently with like minified JavaScript. It's all on one line, and the column number is like 1,000,000 something. VMCPP. So U32 is the way to go. Hops. Oh, these are size T at this point. Okay, so I think here we're just gonna cast them down to U32, but we can be good boys here and just verify. Hops is less than or equal to numeric limits. Yeah. Should be okay. This is not a hot path, because if we are on this path, it means that we're just about to cache this lookup, because we are saving an environment coordinate so that we can cache the number of hops so we don't have to compute the number of hops again in the future. So it's okay to do a little bit extra work there. It compiled. It runs. Well, that's just lovely, isn't it? Cool. So now I gotta build a whole thing. It's gonna take yet another hot minute, but what can we do in the meantime? We can look at our diff and admire the simplicity of it. Yeah, just turning those into U32s. Yeah. Okay. Yeah, let's do a commit here. Shrink environment coordinate. Environment coordinate cache. Instead of, two things. We'll do two things here. This patch does two things. First, we now use U32 instead of size t for the hops and index fields. In environment coordinate. If this means we won't be able to, this means we're limited to 4Gs, to a 4G nesting level, to an environment nesting level of 4G. Right, nesting level and variable count of 4Gs respectively. I think that's okay. I think that's I don't have to say I think that's okay. I think that's okay. And then instead of wrapping it an optional, environment coordinate now has a custom valid invalid state using magic marker value. These two changes combined reduce size of identifier by 16 bytes. Yeah, that's really, really nice. So let's see where that puts us now that we have done those. Because we never tested the argument index mapping change with heap track, so we're gonna get two changes now for in the next test run. But I think that's gonna be okay. Okay, so we're good. And then here, I just want to heap track. All right. Okay. Kind of want to go and find the, if I did a WebKit commit with my Twitter, I feel like I did. But did I? Commits. Ooh. Look at that. July 2013. 2 days in a row. What did we get? 921 kilobytes progression on Twitter. And 886 the next day. Look at that. That's nifty. Hacking on the JIT compiler. No, this is like the value profiling and something about the third tier JIT compiler. Anyways, that's pretty good. So let's nuke it. So yeah, you could see the difference. Like 900K was the scale of improvement, whereas we were getting substantially bigger improvements here. So now we are down to 234. That is just nifty. Yeah, this is not the best view because it's kind of weird. The mouse behaves in a weird way. Hello, 233, 234. We are down. What was the original value? I already forgot. 330. So we're almost 100 megs down from where we started. That's really good. And the previous one, we were at 253. So from 253 to 234, just a little bit of back of the envelope calculator usage here. 330 minus 1, comma 1. Like that. So we're down 95.7 total today. Very, very good. And the last two identifier changes, they got us how much? 253, 6, 19.2 megs. So basically exactly what we expected. 9.5-ish, 9.6-ish changes, which of course then is something like another 7.5% reduction just from the previous two patches. So just super, super cool. Yeah, so plenty more where these came from, obviously. Like if you go through this list here, sort by peak, then you can find lots and lots of things. And if you drill into them, you'll find opportunities and interesting things we can do. It's absolutely something that we should look at going forward as well. The trick, of course, is to not get crazy with complexity, but to do reasonable, maintainable optimizations and simplifications so that you don't overcomplicate the engine to make a small gain, but rather I prefer whenever you can simplify the engine to make a big gain. That's preferable. And we are absolutely at the stage in the project lifetime where there are big gains to be made with simplification. So yeah, I think we're going to end here for today. I'm very pleased with the results we were getting, like 95 megabytes saved on Twitter. Very, very good result. So yeah, this will be the end of the video. If you made it here, then thank you for watching, for hanging out. I hope that you saw something interesting today. Maybe you saw Heap Track for the first time. It's a very cool tool, so I encourage you to check it out. And I guess I will see you all next time. Bye.